What is the why have this machine? Like Rob asked a good question once before. Why have the AA, right? And we answered it in the metals. Why have the FTIR? Anybody? Why have the FTIR?
Yeah, it's really nice for functional groups there.
Yeah. Just if you want to know if a functional group is there or not. But can you think of? You've touched on pretty much every machine upstairs, but you can imagine what the HPLC will do. But is there something that this machine can do that the others can't? I'm just kind of thinking aloud. I think if you synthesize something, right? And if you want to, I'd say more for a research kind of thing. First, you're synthesizing something, think of it really big, so that rules out the GC, right? And then if you wanted a quick answer for something, right? The HPLC is not going to tell you whether a particular bond's there or not. Assuming you just have the diode array detector, they're like a UV vis hanging on the end of it, right? Forget the AA. The NMR might help you out, right, if the FTR can't get it. But I think, yeah, if you're interested in seeing if you actually made a particular compound, and you're interested in this one little bond, right? You're trying to flop out inorganic. You're always trying to remove you have a leaving groups, and then you have other stuff coming in to react. So you know that one spot. And maybe that this FTIR, you know that one functional group is right here. Do you get that peak or not? Maybe that would be something that the FTR could do that others can't. Anyway. Okay, so let's start with Adriana. So just read it and then give us your best shot.
What does FTIR
Don't know.
Is the FT the same?
Yeah.
FT is what? Fourier transform. Yeah. There you go. Okay, keep going. Who's ever next here? Yeah, in layman's terms, though, Kathleen, what is it? What is it? Yeah, it's part of the electromagnetic spectrum. It's called infrared, but in layman's terms, what do we also call this part of the electromagnetic spectrum? We hardly ever use the word infrared. Right? Damn, that thing was hot. Heat. Heat. That's a general layman's term for infrared, I think. Okay, Ricky, keep going.
Why is there a break in the scale in all FTIR spectra at 2000?
Yeah.
I was kind of thinking about that myself.
Do you recognize the break first?
I never knew there was a break.
See how this is?
Is that the line that's drawn upstairs?
This is 1,000.
That's crazy.
You have to really zoom in and see this. This is 1,000, and then on this side of 2,000, that's only, I think that's supposed to be 1,800. I can't read it that well. Is that 1,500? Okay, that's only 500. Okay, so the step above 2,000, it's going in, in jumps of 1,000. On our scale there, below 2,000, it's going in jumps of 500. And it's just, yeah.
There's no functional groups that absorb in that region?
You're getting there. Combine what you said with what Rob was mumbling here.
I said there was a lot more stuff down there.
A lot more stuff. But the stuff is functional groups. Yeah, a lot more functional groups. So they just want to zoom in here by increasing the resolution. That's all they're doing. It's just like zooming in. So it's just a convention. It's how, just historically, that's how people expect to see these IR spectra. Because there's a lot more stuff going on below 2,000, a lot more functional groups.
So nothing absorbs at 2,000?
No. Stuff can absorb at 2,000. It's just tradition, that's where the break is. Tradition. So it doesn't have to be 2,000. It could be anything in that region, but 2,000 is a nice round number.
And 1,500 and below is the fingerprint?
So really, 2,000 and below would be called he just used the word, the fingerprint region, all right? Okay, because that's really where all the details are. So you could zoom it up even more, and you can on the IR. Okay, so I think that's a good term, right? Below 2,000, that fingerprint region. But that may not really get the point across. The point across is better, probably what Rob said. That's where more functional groups are located. Okay, Pavel, keep going.
What's the dipole? So electronegative and no.
You're right on, man. Keep going.
Electropositive atoms.
Not atom.
Other
Not atom.
Elements.
Atom is just a single thing, molecule. He has the word molecule and electronegative in the same sentence. This is really, really close.
Electropositive.
Oh, you're doing so good. Anybody help him out? This molecule has two atoms that have different electronegativities, right? Now, so a dipole is just what? How would you explain it in your own words, though? That's how it's created, is this electronegativity difference. But it's really what?
It's a bond.
Positive and a partial.
Yeah. Electrons are hanging out more in one region than they are in the other region, right? And unequal sharing of electrons. Okay. Do all vibrate... Oh, I'm not supposed to read it. Keep going.
Is an IR active vibration?
Oh, no, sorry. We're at this one.
What is?
Do all. Oh, sorry, I changed it.
You.
Do all vibrations absorb IR energy? You can kind of read the further questions and answer it, but...
Do all vibrations absorb IR?
Oh, look at the next one. Just to give you a hint. Because if there's an IR active vibration, that means there must also be an IR inactive. So would all vibrations absorb IR energy? Then the answer is no. Yeah. Okay, so you're Andy. Just following this though. I'm not sure how I change it all on yours. Okay. IR is what you said. It's actually absorbs. It's an IR active vibration. It's allowed, yes. Yes, but what's going on? That's the real thing I'm going after. Is what's going on for that? Why would one vibration absorb IR energy, another one not? For example, oxygen gas will not give an IR active vibration, an oxygen molecule. However, an HCl molecule will. It's a hint.
Is that different dipole?
There has to be an oscillating dipole.
We did it on Spartan.
Yeah.
All right?
It showed us the different vibrations depending on how electronegative one of the atoms were. The dipole would be moving faster.
Okay. Good. So there has to be an oscillating dipole for there to be an IR active vibration. There has to be an oscillating dipole. And that's pretty much everything, right? As long as those two atoms in the bond are different, you're going to have an oscillating dipole. Okay? But there will be some symmetric things, and we'll see them. But here's some general, most common types of vibrations, right? So, now come on, Rico, what does the little plus and minus thing mean? Look at that. See, I think the arrow, that kind of makes sense, right? It's actually moving. But what do these mean? It's not charge. Oh, yeah. Read the note.
It indicates motion from the page
Toward the reader. So plus does. And keep going.
Indicates motion away from the reader.
And minus indicates motion away from the reader, right? Okay. All right. Emily, keep going. Yeah. kind of bad luck. F equals, do you remember what it was? Traditionally, something times X. Anybody help her? K. What was the K called? Spring constant. All right. How, okay. Sandy?
What is different between two bonds and one has a larger K value?
Exactly. The force is going to be different. There's words that we use to describe this, though. If one bond, think of it this way. What words could you use to describe those two bonds? Ooh, short. Which one would be shorter? The double bond, right? What else could you use to describe it?
Floppy or not floppy?
Right? Floppy or not floppy? Which one would be floppy? CH. Okay. Which one is going to have a bigger K value?
CO, isn't it?
Yeah. Okay. Robert?
Vibrational energy is even with space. I'm going to say no.
Well, look at the diagram.
Oh, I thought the top line was normal. Okay. Then yeah.
Yeah, they are. They are. Ashley?
Each type of vibration has its own individual set of dipole as illustrated in the diagram.
Yeah. Back to, Anna. Just read to the first question and try to answer it.
Vibration of energy looks like an energy level. How does a vibration talk about the same energy level? What do you think is?
No, stop there. Stop there. First question. One question. It has to absorb what? What would it have to absorb? It's vibrational energy ladder. Right? What would it have to absorb? Energy. What type of energy? What type of energy? Anybody?
Vibration?
In the electromagnetic spectrum,
R.
infrared energy. And how much infrared energy would it have to absorb to travel up that ladder?
Yeah, however much it takes to get
Exactly. Look at, pick one, right? Pick one. It wants to jump from that one. Well, I'll get rid of the double arrow here. It wants to jump from maybe the bottom all the way up to there, right? It would need that amount of vibrational energy. Now, is that allowed or not? That's up to PChem, right? Not all transitions are allowed, okay? But it has nothing to do with the oscillating dipole. That's something else. But, yeah, it just, okay. Keep going, Adriana.
What do you think is different about the vibration as it travels up the ladder? What changes?
So it absorbed some IR. What changed? It absorbed the right amount of IR that we're talking about. What changed with that vibration?
The distance?
It has to be more energetic, right? Because it absorbed energy. But if you're actually looking at it,
This huge.
On the graph you mean?
well, you get what with the vibration, right? We've got a bunch of them you can picture in your head going on here. What changes? Does it jump to a whole different one? frequency has to stay the same. That's a good one.
Oh,
Alice has a really good point. If you jump and change frequencies, that means you're a whole different set of energy levels. We're not going to a whole different set of energy levels. We're sticking to this one frequency. So what happens to it? You can't change the frequency. What happens? It's the A word of a vibration. Remember we had this hanging spring. Amplitude of the vibration. The amplitude. What kind of height? Yeah, right? The amplitude of the vibration increases. Okay. Can it move any faster? Is it moving faster? Picture that hanging spring. Is it moving faster?
Are you talking about oscillations or are you talking about velocities and strength?
Is it moving faster?
Because in the middle would be travel.
Is it moving faster?
The frequency?
You can change the question as much as you want. I'm asking you, is it moving faster? It absolutely has to. Because look at now, the amplitude is bigger. You can't change the frequency. It's got the same amount of time to get from here to here. It better be moving faster. But that's the whole point, right? Remember, when you add heat to something, things move faster. We like to think of, flying across the room faster. No, there's different types of motion besides flying across the room, right? Here's one of them, vibrational. Okay, so all this is going on. Who's next here? Question is, what's louder? What stays the same? Frequency, exactly. Ricky.
Vibrational energy levels are numbered using
We're right.
number.
We're right here.
Good.
It's not in our book.
Well, then I guess
Oh, okay, we'll just read this.
Oh, what? Okay, I guess it's different than here.
I added it this morning.
Oh. How does the vibration go down its own energy ladder? Is it by emitting ion energy? Oh, how does the vibration go down?
Now think about that option. Deduce it. Is that a possibility? Emit IR energy. Emit IR energy. He's talking about changing the direction of that arrow, and we're going to emit IR energy. What types of molecules emit electromagnetic radiation? What was the general property of a molecule that can actually emit light? Aromatic, rigid. We're talking about what going on here? Vibrations. This is not a very rigid activity going on here. So just by deduction, is it a possibility or a good guess to say emitting radiation? No. Try again, Ricky. Now, we had some words that went with this, some fancy words that went with this. But you can use the fancy words or you can use the concept. How did it go down its energy ladder?
Frequency?
We can't be changing the frequency. We're just lowering the amplitude. It's dispersing this energy. It's called
Relaxation,
vibrational relaxation, right? But what's going on there? It's just these molecules that have a higher amplitude colliding with other things and just transferring the energy. What is heat? If you talk about, you have a bottle of water here, I add some heat to it. In general, all the molecules are just what? Doing what differently now? Moving faster. Now, it doesn't have to be translation. It can be vibration, too. So it's just right? It disperses the heat. And if you want the little bottle of water to cool down, it has to transfer the heat to the tabletop or the surroundings or something. That's the point. You can travel down the vibrational energy ladder just essentially through colliding with other stuff and dispersing your energy. Okay? It's energy of motion, so you could use the word not potential energy, but kinetic energy. You're dispersing your kinetic energy. Okay? So there's a number of ways to explain that, but How about this last one? I also added this one. We're at Pablo.
It's possible to transfer to the
Is that possible? Now, we also had a fancy word for this. Do you remember it? And we had to have a little,
Oh,
and they were kind of good about it too.
internal and external conversion.
Yeah, it's this word internal conversion. And what I really liked about it is they were really setting us up for this. You have a whole nother, you could draw another one of these guys, whole different frequency. Has its own set of energy levels, right? But notice how if one of them lines up, right, has the exact same energy, ooh, he can jump. He's vibrating now at a whole different frequency.
So does that mean that the frequency doesn't
Okay. Well, he didn't notice. Hang on, no. He's lined up. Did you lose any energy? No. Right? He's lined up. That's how we jump from one frequency to another. Okay, one of those amplitudes, right? They can't oscillate at any amplitude at once. It's very weird. Quantization is very weird. It's like having that spring hanging there, and I can only pull it down this far or that far. That's it. Well, you can pull it any distance you want, right? So it's very, very weird stuff. Okay, but picturing this is one way how you can actually keep lowering yourself, right? Then you jump to another frequency where they're lined up, where this guy's well is even lower, right? And then you keep, right? So things just can get down all the way down to a ground state, as low as possible there, the lowest frequency. Okay. Oh, where are we at? I got Alice.
Vibrational energy levels are numbered between a constant and the transition Ftir,
Yeah, good guess. Right? Okay.
You just told me this.
And that's an example of a selection rule for vibrational transitions. So the one that we drew here, is that an allowed transition, Randy? Is this an allowed transition? No. It's not going to happen. It's not allowed. Okay, so just how many different vibrations can a molecule have? Right? Depends on the degrees of freedom. It's mathematical. If you want to describe the position of all the, where is this molecule in space? You need to say where, since we're talking about vibrating, not only you have to say where the molecules in general, you have to say where each bloody atom is in that molecule, right? So n would be the number of atoms, and then you need an x, y, and a z point for every single atom in that molecule. So the total number of points would just be the number of atoms times 3, right? It's not that complicated. How's that complicated, right? So does that make sense? To describe where a molecule is in space, each atom in that molecule, you need to give an x, y, z point. Well, the total number of points then would be, 3, because each atom needs x, y, z, so 3 times the number of atoms. Okay. So they call that the total number of degrees of freedom. I don't know why they use the word degrees of freedom. There should have been a more constrictive word, but that's just how it is. It's not very visual. But the number of degrees of freedom, mathematical points used up to describe molecules' translation in space, is going to be 3. Oh, it's going in this direction, x, y, z. And then you also have to describe its rotation. They're really just kind of divvying up energy here, but number of degrees of freedom used to describe molecules' rotation. Well, if it's not linear, you're going to use up 3. If it's linear, you're going to use up 2. So the degrees of freedom that remain for vibration, right? So 3n minus 3, 3n minus 3 would be 3n minus 6. 3n minus 3 minus 2 would be 3n minus 5, right? And that's all the vibrations. So that's how many vibrations you have. Okay. For example, if you have water, this is going too deep, but just to finish the story. If you have water, how many atoms do you have? 3. Okay. So you you pretty much have to draw a Lewis dot structure of water or do a little Spartan thing and find out that a water molecule is linear or bent. It's bent because I have those lone pairs pushing stuff down. It's bent. So if it's bent, let's clean up this mess here. How many degrees of, well, 3 times 3, I've got 9. Okay, minus 3, and it's linear or nonlinear? It's nonlinear, so I got a minus 3 again. 9 minus 3 is 6, minus 3 is 3. Okay, so when I click on this guy, we're going to see 3 different types of vibrations. Okay, that's it. That's all it has. That's all it has available to it. So let's take a look at this. Hopefully he's going to work here. Whoop. Okay. And they kind of match the diagram, right? I don't see any that are going in and out of the plane, right? They're all just doing their little thing there. Okay. We have carbon dioxide. Okay. Carbon dioxide. It's vibration. So each type of vibration has its own frequency, right? And if it absorbs that frequency, it just jumps up its vibrational energy ladder, and the amplitude would what? Increase. Yeah.
So do they only ever show these with ball and stick model? Because I'm trying to picture it with, how they do it.
Spartan would.
Yeah.
Spartan would. This one is a stereo image. So if you really want to see what's going on, you have to cross your eyes. So I don't know if you want to do that or not. My mom always said they won't go back. So I don't do it. But I don't know. Some big.
Oh, okay. Yeah, so that one's going to help us.
Did you cross your eyes to see it?
No, I can
Just picture it?
Yeah.
Okay. All right.
If
What
I
is?
cross my eyes, I just see 4 of them.
This is iron 3, the pentahydrate. Okay. So how does an FTIR spectrophotometer get an IR spectrum? Inside its guts is probably the most sensitive instrument you can build with your own 2 hands on this tabletop, an interferometer. And in PChem, you're actually going to build one. You can, most sensitive, what I mean is sensitive to motion, to changes. And what it has is it has 2 mirrors. There's a mirror here, and there's a mirror there. But one of them is you can just slide back and forth, and it changes the little image that you get. And you get an interferogram. You get all these lines, right? And they're going to change their spacing depending on where you have the mirrors and things. But it's kind of fun to play around with. But you could actually, if you really zoom up on it, right, and someone closes the door upstairs, you can actually see it vibrate a little bit. Okay, but
So you get a plot before you get the sample?
so what they're doing is they're getting this interferogram going, and you're right. This light is striking the sample, and some frequencies are being attenuated in it, and it figures out what those frequencies are. So all that information is in one little interferogram, but it's going from the frequency, in this case it's kind of the distance in the mirror or the intensity of the interferogram to the frequency region. But so it's doing this Fourier transform to go from one domain to another, but it works, and I can't really go much further than saying that. I mean, it's pretty much if you build one, it makes more sense. But actually, that's why in the machine it says, please don't move me. There's moving parts, because if you slide it, and I did that once, I forgot, and I heard the mirror go dung, right? Because it's sliding back and forth there. Okay. What do they use as a source? Now, when you pop your stuff in there, you saw that little laser, right? Is that the IR source?
Isn't that just
No. That's how you can line it up, because you can't see IR energy. In the older ones, right, you had to have a little IR card, and you had to put it in there, and you'd see the IR energy. But here, they just have a laser going through there. You can see the path. What's the source? It needs to be something that generates a whole lot of what? Heat. So what generates a whole lot of heat? A wire, hunk of ceramic, just anything, right? And you want it to be able to heat up and cool down many times without, getting wrecked. But they call it a glow bar. I think what we have is a glow bar, but I'm not. Just pretty much a wire. And stuff that we can analyze with the FTIR. All right. This is probably should have been first, because we tried to answer the question, what's something that you could do on this machine that you can't on the others? And here's a good number of them right here, right? We can't do solids on anything else, right? Powders, on liquids we can, even mixtures, but solids, man, yeah, that's a good one. What's this? What is that? It's this stuff, right? You go down to Corpus Christi, and you can find these things. There's research posters out here on that. Okay, they say it's becoming a real problem in nature. Alrighty, that's about it. And we finished early to make